this class we are going to discuss about affinity chromatography, or sometime we'll term it as bioaffinity chromatography, because most of the time we are utilizing here the property of biological molecule to identify, to have the specific affinity to some of the compounds. So it is very much specific in nature and mostly used for bio-based material. Now in this case, it is actually a reversible and biospecific interaction between a molecular species and its ligand for isolation from a biological milieu. So maybe we are having more than one or two or three or 100 compounds may be there, and if we have something very much specific interactions, or if you have some specific ligands, then it can actually interact and it can be separated out of the broth, maybe, which is actually a mixture. Mostly we are discussing about protein. The protein to be purified or quantified is specifically and reversibly adsorbed by the complementary ligand, which is immobilized on insoluble matrix. So we know what is the ligand's molecule we have. We are going to make it binding with a solid support, which is insoluble matrix, and we are loading our sample. So those specific molecules which are interacting with the ligands will be retained, all other non-specific binding will be cleared out. For example, here antibody antigen recognitions can be there. Similarly, we can have lectin polysaccharide binding, nucleic acid heparin interactions, and some recombinant fusion tag and proteins can be also utilized in this process. Now we'll be showing what is the basic working principle for affinity chromatography, or how really we are working, maybe working model. So you can see here the 5 or 6 different stages which are normally utilized in this case. We can have the affinity ligands are covalently attached to a chromatography support material and packed in a column. So we know what are the ligands we are going to have. We are functionalized already the packing material in our matrix. We are loading in a column. Once it is loaded, then we are actually putting our sample. Sample is actually mixture. There are different compounds present there. So samples is flow through the affinity column along with its binding buffer. So specific compounds you can see is already attached to the ligands molecule, which are non-specific is actually coming out. They are simply not being used, which can be washed through the column to remove those unbound things, and then we can actually change the buffer, or you can use the elution buffer to maybe disrupt the interaction which was already there, and we can recover the purified target molecule. So essentially we are making preparation of the ligand attached support material. We are loading our sample. We are cleaning, or maybe the washing of the unattached biomolecules. Then we are releasing with some elution buffer which is coming out from the column, and this is the final step for recovery. This is the procedure normally adopted. Now what are the advantages of bioaffinity chromatography? It is extremely selective in nature. So we know specifically what kind of molecule is going to bind. So that affinity can be very much specific, including it can be either some group level or even specific molecule level. It is possible. There is a good purification and more than 90% recovery in a single step. It is possible. So the degree of purification in a single step is quite high, which is very much attractive and advantageous for bioaffinity chromatographic system. High concentration effect from large volume mixture. For example, if I am having some kilogram, maybe some 40-50 kilogram, I am having some milligram of your target compound, that can also be recovered effectively. So this is really good because we can concentrate the material significant amount, which can be used to remove the unwanted material also. So we can remove the unwanted material very effectively, because if we retain only the target compound, very easily the unwanted materials can be removed. So both way we can do, either purification for our target compound, or we want to remove the unwanted compound. Actually essentially same. And the way the interaction is going to happen, or what are the specificity is present in the interacting molecules. It can be of van der Waals force, hydrogen bonding, or hydrophobic interaction. There will be some equilibrium constant for binding, because any case we already know, for example enzyme and substrate complex, so there will be a binding constant. So A and B binding will have a reversible process, so one is K1, another is K2, and we can find out what is the ratio between the forward and backward reaction. That is actually the equilibrium constant for binding. This value is very important, because if the K value is very high, that means it is strong binding is there. If K is very low, then it is non-specific binding and adsorption may not take place really. Here we will showing the different kinds of ligand molecule and what are the target molecule which it can bind. So for example polymyxin, if we are using as ligands, so the molecule of endoproteins can be separated. Similarly biotin can be used for avidin, streptavidin compounds. Gelatin for fibronectins can be used. Lysine for RNA or double-stranded DNA, lysine can be utilized. So on. So there is actually long list. Some are very much specific. Some group of compounds can be separated. Now, what is the basis for choice of support or matrix or ligands molecule? So support should be high surface area. It should be water insoluble. It should be rigid. In the same time, it should be permeable, microporous with reactive functional groups. It should be stable, and it should have minimal non-specific adsorption. So other compounds are not really binding with it. It should be taken care. And what about the ligand compound? It should be available which can be modified. It should have the functional groups which can be modified for binding, because ligand has to bind two things. One is your support matrix, it has to interact, and your target compound. Its affinity values should be around 10 to the power 4 to 10 to the power 8, so strong binding is possible. A ligand should have amino, carboxyl, thiol, hydroxyl group to bind to the matrix, we already told, because these functional groups will actually interact. Maybe covalent binding with your matrix is required. It should have multi-point attachment. So if it is having a multi-point attachment, so binding with the matrix will be strong and it will be irreversible binding, so stability of the attachment will be high. Sometimes we need to have some spacer arms also, because we'll show you why it is important. Because we need to have the coupling of small ligands to matrix. So sometimes we have seen it is having low binding capacity. The reason can be steric hindrance. Steric hindrance means, for example, this is your matrix and we are for example we are attaching our ligands like this, and you see, for example, these are the target molecules. So it may happen that the close proximity of those ligands which are coming, which are binding with the matrix, they are enforcing those specific molecule to come very close to each other, which is not possible. So steric hindrance is there, binding is not really good. So what can be done in this scenario? We can take out those ligands and we can put some spacer. So flanking end, you can see we are putting the spacer molecule which is giving some extra gap from original one. And now if it is the spacer is there, the molecule or target molecule can bind very easily. So spacer is actually increasing the distance from the matrix, so the steric hindrance can be avoided. Most of the time it can be a linear aliphatic hydrocarbon chain, so and it should have some of the hydrophilic groups as well, and it should have the functional groups to bind with the matrix, bind with the ligand. So we can have for example we can have sometime hexamethyldiamine, we can use 6-amino hexanoic acid you can use. So this hexanoic acid is actually hydrophobic chain which is there, and 6-amino is going to give the functional lights to bind with the ligands molecule. But if we are having very much excess spacer group, it can also have some undesirable effect in the binding process. And how we are doing the chromatography, in this case affinity chromatography, how we are doing, it is actually protocol rather I will say. So first thing will be adsorption of the desired component. We are loading less than 5% of the bed volume, so you should be careful on that. Then you should wash with some high ionic strength buffer so that unadsorbed compounds will be released. Then we will be using elution buffer where the bound compound will be relieved, which will actually alter the equilibrium of the binding, or specifically, non-specifically, it is going to weaken the strength of the binding or association. It can be done by changing pH or changing ionic strength. Some denaturants we can use, some geotropic agents we can be used like urea, guanidine hydrochloride can be used to aid in the elution process. And then we need to regenerate the column. The column regeneration can be done by washing with several bed volume of tris hydrochloride, which is pH 8.5, along with salt concentration of 0.5 molar, and then it is washed again with 0.1 molar sodium acetate, pH 4.5, along with NaCl, re-equilibrating with our starting buffer. So one is alkaline condition, another is acidic condition. We are washing the column for regeneration purpose.